I'm really excited to be here. I'm excited to, I'm a very generous introduction, but I'm really mutually a fan of Yad's work, and I'm really excited to be in a community where people are trying to think about the nature of computational intelligence and collaboration, and so anyway, I benefit from your thoughts. So I would say I erred to kind of pack in more projects and perspectives so that they could be hooks for conversation either today or tomorrow, and then just coherently rendering one project, although I will render that project. So with that, yeah, so accelerating science with human-aware artificial intelligence, and I'll state what I mean by human awareness. And there are, I would say, a range of different kinds of things, but it leads to a way of thinking about complementary artificial intelligence, or complementary intelligence more broadly. So I've spent a fair bit of time thinking about and trying to drive also questions about different kinds of scientific intelligence and epistemic standards that drive science in different kinds of ways. And this has largely been a conversation with science policymakers and science funders, which I'll mention a little bit later. Wow. Okay. So I've for example, in the U.S., Congress recently kind of mandated this Chips and Science Act, and I'm the research director for this kind of critical technologies kind of advisement or advisory network that thinks about some of these kinds of things, which I'll bring up a little bit later in examples. And I run a center called Knowledge Lab, which is really focused on, I'll call it a kind of a complex systems view of knowledge. And by complex system, I just really mean that while the knowledge stack, if you're thinking about some kind of pragmatic model of knowledge, which is kind of driven by action values right at the bottom, and so this is shaping the sensations, representations, understandings, et cetera, that you're engaged in. You're also constantly engaged in conversation and collaboration with other actors, where you're borrowing their understandings as explanations, you're importing their sensations as your data, et cetera, which effectively makes you this kind of complex set knowers. And so we'll be thinking, I would say the lab is really focused on thinking how collectives and systems think, and how relative to specific values that they might have, can they think differently or think better. So I would say the provocation for today's talk is really what kind of an AI do we want? And especially in this context for science and social science and humanistic inquiry. I don't mean science in a particular dominant framework. So do we want the classical notion of an artificial intelligence, which I would say is really spawned by this Turing imaginary, 1950s, the 1950 paper, Computing Machine Intelligence, where the imitation game captures this idea that basically, human intelligence is the standard of intelligence, and we're trying to effectively approximate the standard in reasoning activity. And this kind of gets even more extreme in 1959, and really throughout the 1950s, when Samuelson was kind of building these checkers playing engines, and the idea of machine learning, where you're not just matching the outcome, but you're also matching the idea as this thing is going up is that, so we think about artificial intelligence more broadly. There is a kind of a humanoid intelligence, rendering, which I think is arguably neither the most efficient nor the most ethical way of thinking about generating artificial intelligences. Why is it not the most efficient? Well, because for any task on which we're competing against other people or against nature, then basically reproducing human possibility and limitations ends up, putting us back in a place where we're at a very similar point to where we were before we generated this intelligence. And ethically, we're basically designing, a bullseye on human capacity. So the idea is with science, with 8 million researchers, that if you're focusing on replacing human capacity, then you're going to build bots that replace rather than expand human capacity. So it decreases the value of human research capital, but again, it doesn't expand really the broader cognitive space of possibilities. And so how do we basically build things that help us think differently and that allows us to think differently together. I have a cephalopod here, I'm a big cephalopod fan, as a creature that kind of is not the most alien, but perhaps they're more closely related to clams than to us, but they have rich intelligence and it's distributed intelligence largely. I would say this is different, or it's an extremely radical version of the augmented or the amplified intelligence argument. It's interesting, amplified intelligence, like the same AI was posed by Ross Ashby the same year that artificial intelligence was formed in 1955. This idea that I would say is most expanded with Doug Engelbart is like, how do we augment the human intellect? And it's really about, there's many ways one can imagine augmenting. This augmentation, which is all about interfaces, it's all about screens and mice and file systems, or you can imagine that neural links, like in the modern imaginary, are really about unmediated manipulation of information. So how do we reduce the transaction cost so that we can just think faster? So this is, if humanoid robots are the embodiment of artificial intelligence, then these kinds of interfaces are the embodiment of that brand of augmented intelligence. And I'm just suggesting that this is, again, not going to allow us to really advance and create something that's radically different from ourselves. How do we build something that thinks differently? I mean, an augmented intelligence approach it thinks more like us and allows us to think faster, so it's largely redundant and efficient, but it's really thinking small. How do we think differently? How do we think bigger? And I'll really argue that the potential is to build complementary intelligences that radically augment intelligence by being different from us, right? By facilitating conversation across these boundaries. And I'll talk about three kinds of designs in which these kind of complementary or alien intelligences, friendly alien intelligences, can be used. Now, these are all human-aware intelligences, so they're not so disparate that they can't engage with us in some meaningful way. And I'll go through talking about, both what are some of the desiderata, how do we build things that are diverse relative to ourselves, what are some of the dimensions that we might think about in that construction, and then I'll go into these cases. First, I'll talk about AI collaborators. How do we build kind of diverse collaborators? How do we build diverse coaches, which is to say they coach us to become cognitively more different, relevantly different for the project at hand, and AI coordinators that basically assemble either different machines or machines and people or people in such a way that we achieve greater collective outcomes than we could have or would have otherwise. So that's the kind of overall design. So it's kind of 4 chapters. One is like, okay, how do we think about these radical intelligences just from our understanding of their existence in the space of science and the world, and then how can we go through a series of designs that allow us to think about designing and cultivating such AIs. So I'm not going to spend much time given our time, but so one can think of a kind of wisdom of crowds logic. So this is Francis Galton, who was a geneticist and a eugenicist. I mean, all geneticists were, eugenics was like the public policy of genetics. And so he was expecting that basically the tail of the distribution of intelligence would explain the most. And what I love about his paper, Vox Populi, is that he was so utterly wrong. And that he published and celebrated the paper, which is this simple survey experiment, quote unquote, in which he goes to this West of England fat stock and poultry exhibition. There's a dressed ox. It wasn't a living ox. It was a big bag of meat. And people could go on, 800 people, kind of wrote down a poundage. And the one that was closest would get the meat. Now, the thing that was surprising to him, and surprising to his sensibility of looking for intelligence in the tail of the individual distribution, was that the mean was less than 0.1% off. It was 1 imperial pound off The median was 0.8% off. So the mean was closer than any particular guess. There was no intelligence that was more intelligence than the crowd. And I think what he didn't recognize, but I think has been widely appreciated in the last 20 years, is that it's not like I wasn't at this fat stock and poultry exhibition. You know what I mean? Like, I don't know anything about, the side, but everyone who was there either had a cow or fancied cows or oxes or auctioned them, or like all of them had different. What does diverse data mean? Well, let's say I have an ox of X size. I know what the weight of my ox is. I can look at this ox relative to my ox. And so we've got diverse data and diverse kind of algorithmic approaches, which facilitates this kind of collective wisdom. And so, of course, there's many ways in which we can be diverse, cognitively, perceptually, experientially. Typically, I'm a sociologist, people think of it in terms of identity. Here, even though identity often correlates with some of these other diversities, these are the ones that I'm going to lean on in this context, not because they're not critically important, but just because this is where the data investigations that I've played have worked. And so we're going to explore this wisdom of scientific, technological, and kind of business innovating crowds. Right? So how does one think about cultivating these kinds of diversities? Now, so big data in scientific and cultural investigation allows us to think about how science thinks as a system and build these type data-driven models that allow us to investigate it and consider alternatives. And so I'll kind of spend a little time on that before I dive into our designs. I know I don't have a ton of time, so I'll whip through this. So one project in which we try to understand how is it that science explores as a system is we basically try to basically predict future papers, and not particular papers, but every paper. So every paper, in this case, is an impoverished representation. Every paper is just like a bag of keywords or a bag of context, like unique journals or conferences or conversations that you stitch together, you pull together. So here, I basically place these inside of a mid-dimensional manifold. So this is like a 40-dimensional manifold. And I wrinkle this manifold such that it maximizes the likelihood that a Poisson draw from the manifold will produce the papers that were produced in that year, right? That's the game I'm playing. And then I can basically allow this manifold to move with Brownian motion. It's random motion, but it's contextually appropriate random motion. So it assumes effectively that investigations will be smooth within this space. I predict next year's papers with that moved or evolved space with AUCs of between 0.89 to 0.94, which is to say that most science is highly inertial, unsurprisingly, right? Because people who exist over time produce science over time. Death is an emergent state. So this is the game that we're playing. We're generating this most predictive model of science, and then this allows us to identify the least predictive things, which is to say the most surprising things that show up next year under this. So the most unexpected things under this most expected model, this most predictive model, right? And these surprising things, the things that are surprising to this model, are also surprising to the human scientists that are engaged in these investigations, that are themselves, all of us, trying to predict what the next space of things are going to be. So this is a very highly surprising combination of these keywords, which represent basically the discovery of a set of mammalian functions or functional units that exist in plants, and that kind of reformulate the ways in which people thought about work in that space. So I'm not going to talk about the validation, but if you look at people saw errors and surprise in the same way. This is highly predictive of the things that are surprising to scientists in post-publication review. We looked at this across contexts. After validating the model in the way that I just described, it turns out that higher content novelties, this is kind of surprise in the combination of keywords, is associated with awards. This is basically every chemical, biological, and medical award. Context novelty is highly predictable citations, much less predictable awards. These are Nobel Prizes in chemistry, medicine. Exactly the same is true for physics, which is interesting. It basically means that, they're like median novelty. And the reason is because these awards are given by contexts, right? So the Physics Nobel Committee is not going to give or systematically discriminates against physics advances that violate the boundaries of physics, right? But if you put them all together, if you add content and context novelty, you can predict about 50 to 60% of the likelihood of being in the top 10% of citations. So this is like the best ex ante predictor. So, and the question then comes, where do these things come from? Who's generating these things? And the answer is, to a lesser extent, it's unusual people or surprising people, careers, like a surprising career that brings together unusual combinations of ideas. Also, to a lesser extent, surprising teams, so people who come together who are diverse. But the most systematically predictive thing are surprising expeditions, where people come from one part of the space, aliens, basically come over and they speak to or solve problems in another part of the space. They're publishing things in a space that's never seen people with their expertise before, and they've never seen problems like this before. Now, of course, often they come together. These are highly, it's like, okay, it's not just that it's a surprising event, but you also have surprising people that are stitching together a surprising team. But even when you don't have any of the other things, you have a big burst if you have these surprising aliens, that come and abduct your space and your ideas. Now, how do these surprising things happen? This is a survey experiment where we're actually just sample tens of thousands of researchers, their papers. We ask about particular things that they reference inside those papers with respect to how influential they were, how well they understood and knew those projects. And we find systematically that these surprising combinations occur by accident, which is to say, they're most predicted if you take all these identities into account, if you're at the same institution and not the same department, right? So you're basically, it's not like you go out to a conference, which likely is, everyone's in the same community or culture, but if you're at the same institution and, you share, your kids are on the same soccer team or football team, you serve on the same committee, you bump into each other in the Whole Foods or whatever. So these systematically occurs through these unusual or surprising accidents that come as a function of people being really brought together in the context of these spaces. And it's a challenge because as science grows as an enterprise, and this basically shows as fields grow, it kind of exponentially is associated with a decline in the likelihood that new ideas enter the canon, which is to say the highly cited parts of that canon. So as we become bigger institutions, bigger fields, we basically constrict the space of collective imagination or discussions that occur, which is again potentially problematic in the context of discovery.
So interrupt just
yeah, sure.
Is part of this effect just running out of space?
There are cases where fields speciate, and when they speciate, you see the same increase that you see a decrease when they merge. So I think this is the general question when people explore the slowdown of science. It's basically like, to what degree is like the low-hanging fruits have just been plucked from all trees, and to what degree is it that we have just committed to a set of disciplines that we don't go to any other disciplines where there may be low-hanging fruits. And I think this is an important question, but I think there's very little question that at least part of it's institutions, which is to say part of it is that there are other configurations. If we want to think about a discipline as a set of problems that are most profitably explained by a set of methods, right? A kind of a contract. That's what an education is, a graduate education. It's like, hey, if you study these things, here are a class of approaches that will fruitfully allow you to investigate these things. That's and I think this says that there are diminishing margin returns to those groupings, but there may be many more possible groupings that you won't immediately experience those diminishing margin returns, right? This is I think given my time, I'll just mention I've been exploring kind of the roles that different nations play in the context of science by looking at predictable versus kind of like emerging areas of science. Here we have basically like a plate tectonics model that predicts the likelihood that new combinations of ideas will arise as a function of their movement together. And you can predict in a way that I'll show in just a few minutes, particular people and countries that are sitting in those places that are at the point of the spear of these things. And you find that you could frame, the global scientific investigation as one of competition between something like China and the US, which is very like an existential thing for US policy. But it's silly because what you find is systematically, yes, the US is like continuing to fund technologies and sciences on which it is dominant and which have been consistently fruitful. And China has invested in things that are emerging, and they're long bets and they're low probability bets, but if one of them succeeds, then it would be dramatically useful for the entire scientific space. So thinking about it competitively versus cooperatively really misses, I think, the way in which the world system works as a system. I'll just say that it doesn't really matter the domain that you're looking at. In other cultural domains, this is business. We find now, has anyone started a startup company before in here? Seems like this is kind of proud of, like, imagine that maybe it's like one person had like a pinky up, so he's like ashamed. He did it, but he feels bad about it. It's like that. So okay, I won't say who. No, but the idea here is you have to show a minimum viable product quickly, right? Within say 3 years of venture funding, and so you do. It turns out these companies that are successful systematically combine unusual things, but the things that they combine are already well applied, right? So it's like technologies that are already applied to specific business cases or contexts, and those functional units become the things that if you combine them, you can fail fast and are systematically associated with the likelihood of having, let's say, an IPO or a high-priced acquisition context. It turns out we see this in other cultural contexts as well. This is a project in which we looked at the political diversity of individuals as a function of their contributions, but these contributions predict about 30% of their own ideology and voting behavior. And the more polarization in politics, so basically the variance of their political positions was associated with a high quality of political pages. And now we're engaged in a kind of a large-scale kind of generative recruitment experiment where rather than just observing those differences, we're selecting and incentivizing people to contribute to these pages and finding a similar pattern of behavior. Now, it turns out that not all diversity works. So if we look at where fact-checking and misinformation policing occurs most, it's like a vigilante activity on the web. There's fact checks, and then people will slap other people's ideas, their misinformed ideas with the fact check. The problem is that systematically the people that they slap are not inside the bubble. They're actually systematically exploring outside their bubble. And when they get slapped with a fact check, they retreat to the ideological bubble that they were in before, not that they were in before, but it actually creates these bubbles. So diversity matters, but it's also like civil discourse. There are institutions that can facilitate the integration of that diversity in meaningful ways. I'll say just one other idea before I go into the cases, which I have much less time to do now, is just that the power of thinking about these generative models, and in particular, you can think of large language models as contextual embeddings in which if you place people in these spaces as a function of their prior contributions, let's say this is a space of novels and these are screenplays that each of these characters wrote, and these are two concepts or ideas that are like moving together over time, the likelihood that you are going to combine those two ideas is almost precisely a function of the width of the angle with respect to which you can see those two ideas. If they're converging on you, you are doomed to combine them. If you're outside, and even though you're equidistant from both these concepts, you're blind effectively to the combination of these possibilities, and it scales appropriately. It turns out these are influential not only for positions, about what you combine, but how effective those combinations are. So if you look at, we build a kind of an evolving semantic space of novels and we project in people's screenplays. We build a space of science and we project in people's technology. We build a space of business discourse and we project in people's company descriptions. We find systematically that the diversity of the group's angle with respect to their respective product is systematically associated with improved performance of that project in the community, that product in the community. And it's inversely associated with the diversity, the difference between them. So it's like, the greatest advantage is if you have different angles coming from different directions, but converging in a space, right? Where they're really close relative to each other at that moment, but they come from very different spaces. Right now, I'm working with some folks in Denmark where you have really beautiful, I'll call it exposure data. So we look at every library book that anyone's checked out since the 1960s, every book they read for every class, and you can sample, not you, but the statistical agency can draw upon those people with different exposures, pull them together experimentally and explore the relative likelihood that they would produce different kinds of outcomes with different kinds of performance. So that's okay. So now our cases, which we've got 10 minutes for, but that's fine. I'll just whiz through them, and I'd love to hear your cases. So can we design human awareness into this space so that we can create augmentative, complementary AI that takes advantage of this idea of diverse wisdom of crowds? So AI collaborators. How do we build AI collaborators that are diverse from us, sufficiently diverse that they can expand our thinking? So here's really the paper that's coming out next week called Human Aware AI. So this is a different paper. This is a paper from 2019 where they basically just embed the literature in a very simple words of X style embedding model. And it turns out that if you just embed the chemical and material science literature, it basically discovers many aspects of the underlying chemicals that you talk about, the structural differences, the oxidation of these things. And if you basically look at the relative distance to them not having been combined, so you're basically doing like transitive theory. So, this, copper compound is described with photovoltaic applications, which is indirectly described with thermal electricity. You can infer that that material will have that property. So here we basically built in human awareness by identifying this property. Like, to what degree are there people that could link, say, an entity with a property? And what are places where they couldn't link them, right? These are opportunities, right, where we can basically build in intelligent question askers for which there is no human correlate. No one has been educated at the boundary of these fields and possesses a knowledge of the relevance of a property and the existence of a material. So how do we do this? We just do it simply. Initially, we just take all these papers. They're hypergraphs. Remember hypergraphs before, except this time we include the authors as an entity in the space. And so we basically run like close to 1 billion random walks through the space. What does that mean? Well, it means you start with the property, you jump to a paper with the property, you jump to a person who authored the paper, you jump to another author on that, or another paper by that person, you jump to a material on that paper, you jump to another paper on that material. So the density of the random walks is proportional to the cognitive availability of the hypothesis that a material at one end will have the property at the other end, right? And we know that this actually works, so I won't go through all these details because our predictions are sitting right on these ridges of author density in whatever space that we're looking at. They are, they can prove prediction by using a little bit less data, from 50 to 500% improvements, which are modulated almost entirely as a function of the density of the literature. If you have a super dense literature with like review papers, then you don't need to know where people are thinking. because that's what review papers are doing, right? But if you don't have that, which is almost everywhere else in science, then you get a dramatic boost. And the reason we know that this is why the models are working is because we've got like a 0.4 to 0.5 precision at predicting the particular person who will make that discovery as a function of their prior experiences, right? So this justifies the kind of Brownian motion model. It's like this is the only person or one of two people, likely to come across this possibility inside the space. So that's like the most human model, and I could go through all of our 600 scientific cases that we explore. I won't do a lot of drug repurposing, a lot of thermal effort, a lot of energy relevant material stuff. COVID is interesting because it spun up so quickly that you dramatically improve the prediction of new discoveries as a function of where people are at the very beginning of the space, because no one starts exploring coronavirus treatments or vaccines in new ways. They jump to where exactly basically researchers are in the space. And in fact, even if you have this is a beautiful PNAS paper by Laszlo Berbash and colleagues in which they incorporate about 10 different kinds of protein-protein interactions to figure out which vaccines and therapies are going to be explored. Our system is totally blind to this, and we do much better, right? Even than that, just by anticipating where people will go within this high-dimensional manifold. So that's not a complementary intelligence, that's a scoop machine. That's basically going to steal someone's ideas like 6 months before they publish them. What if we try to maximize complementarity? So now we're generating hypotheses that basically are arbitraging these high-dimensional holes in scientific space, right? There's no people that have discovered them. We have a kind of a scientific plausibility component, which could be the literature, could be first principles models of the phenomenon in question. And then we're trying to discover which of those things could not be discovered by a person as a function of where people are in the space. And the fact that, as we show, people are enormously inertial. And the answer is first, yes, these are complementary discoveries. Yes, if they're rarely discovered by people, but if they are, it's like years or decades into the future, right? It's much longer because the whole system has to reorient before it does that. They're better. They're better. They're better on average at identifying, at building materials that have strong representation for this functional property. And the reason is because, science is like diminishing marginal returns to theory, squeezing out the last possible application, from a particular orientation. If we just go to another tree, right, in the space, we systematically have a boost as a function of avoiding those people, just because people have not been over-harvesting the things which are equally valuable in principle across that space where there are some places of dense human participation and some places of very sparse. So this is another experiment where we have kind of an informal actor-critic structure where we have, generate the title of an abstract in 150 words for a scientific research article about concept 1 and concept 2, which of course we curate very carefully. These are things that have never shown up together. There's a very sparse density of authors between them. No one could have inferred them, or very few people could have inferred them, including a description of the novel hypothesis about the connection. And then we have rounds of feedback where we ask it to evaluate that hypothesis, effectively generate like a review report, rewrite it according to that benefit, send it out to tens of thousands of scientists, and then we're doing two things. One, assessing the degree to which these are interesting to them and why, or provoke other interesting things in them and why. And we also are allowed to or enables us to predict how it is the particular people in the space will see them as more or less novel as a function of their objectively subjective space or position in that space. So here's an example, which I won't share, but it's a real example. So I will very briefly go through AI coaches and AI coordinators. So the AI coach idea is one idea is like, can we create like digital doubles of a phenomenon, right? So these are data-driven simulations of a phenomenon that are sufficiently tight and accurate. And when I say sufficient, I mean it's like the opposite of what I learned in school, which was like necessary but not sufficient models. These are sufficient but not necessary models, right? So these are models that explain almost all of an outcome. We don't know if it's explaining it the right way, but it's predicting almost all of an outcome. And then we can experiment in very coarse ways with those models. This is a model of crime in the city. What does crime mean? Well, crime just is like, you know, it's not that people are doing bad things, it's people doing things that are unlawful and other people assessing and trusting the police enough to send it to them and the police coming. Okay, just a couple of minutes. I know I'm in borrowed time, but you know, this model, which predicts about, you know, 0.93 AUC, basically crime in the city for places that have non-zero crime. So it's not that bad. So here we just increase the you know, the rate of crime in a particular place. Any particular place. These are, you know, all major cities in the US, and we find systematically when that simulated experiment occurs in the digital double, basically all of the crime resources go to the rich areas of these cities. And then that allows us to say, oh, so these are, you know, can we actually observe real natural experiments or stage actual experiments prospectively that allow us to see that same effect, which was not at all obvious ex ante, and then this allows us to identify those things through other natural experiments. And this is not a paper by me. This is a paper by Jens Ludwig and Sendel Molenaken, where they did. They basically analyzed the amount of variation in basically judicial assessments of whether or not people should be granted bail, right? And they find that basically these images ends up explaining much more variation than any other single variable. They basically identify the directions in the images, right? So how do they build the direction? Well, they build a GAN model that basically makes all faces sit inside this high-dimensional manifold, so you can move spaces in this manifold. And then they take the directions that are the most explanatory of the judicial decisions, and they just ask people, what's the difference between this row and this row, right? And almost everyone said, well, it's a grooming difference. Like the people are shaggier, they're much less kempt, they're more poorly shaved in this row than this row. And in this dimension, these two dimensions, it's basically like grooming, and the degree should have a fat or a heavy face. Right? The fatter the face, the more generous the likelihood that you'll be let out of bed versus an angular tight face. And these two things explain more than any other single thing other than gender with respect to the likelihood that the judge will predict an outcome. So again, it's coaching scientists to see things that they didn't see before by identifying these differences in the data. You know, these are simulated survey subjects, and we're using it to kind of discover relations and differences in polarization in societies. These are other, you know, large language models. This is work by one of my students, just him and his collaborator, Bjorn Q. Lee, where they're basically also predicting questions that have never been asked of individuals. Here's an example of a study that we're doing where we identify different questions that are asked in large language models. So you instantiate a kind of an identity. Hey, I am a Democrat, blah, 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 and telling my story. Now, this model was trained in December 2019, before the coronavirus was visible to almost anybody. Now I'm going to teach the model about the COVID context. Now I'm going to give it an issue, which is like a policy direction. Students should be required to receive the vaccine, and then I'm going to prime it, and I think this is a great idea, terrible idea, and then we allow the model to actually code the degree to which this is a good or a bad idea. It actually projects them to an internal representation of that space in a very tight way. And it turns out that this ends up predicting almost 90% of the variation in the ways in which Democrats versus Republicans view these measures after the virus became a significant issue in March and April of 2020. Basically, Democrats were happy with largely mandates. Republicans were really happy with ending mandates, except for border closings. Like, they were, Republicans are pretty happy ending border closings. All these things suggest the potential to kind of create interactive bots. And so now we're basically engaged in work. This is Michael Bernstein's work that shows conversations. We're predicting conflicts and collaborations and trying to run little proto conferences that pull together diverse intelligences and identify things that they suggest in collaboration that these collaborations don't exist in the world. Final idea of AI coordinators is like, what if we put the entire scientific system inside this kind of AI process, and we allow the system to recruit people and actually discover across the space. So this is a social experiment. We're trying to discover optimal combinations of compositions of people for teams. And here we've got like a computational experimentalist, theorist, and what I'll call phenomenologist, this like sampling strategy. How do we pick the next experiment? And then we just unleash this kraken, unleash this beast to assemble optimally teams for these spaces. And we find across different tasks, very different movements. Like this is where the sampling begins, but very quickly it discovers that, for example, you want almost opposite both team size and range of cognitive flavors, right? Cognitive styles for engaging in a creativity task versus a kind of complex operations research style assignment task. Right, so we can just basically allow the machines to basically select the people and actually select the experiments, or we can assemble people together in optimal teams, and we can talk about that more broadly later. Anyway, I'll just close by saying, our purpose here is how to build ensembles of diverse intelligences, a kind of radical augmented intelligence through AI coaching, coordinating, and collaborating to both advance science, technology, and enterprise. And also to think about like regulating other AIs, like this, the diversity of objectives in these AIs facilitates the possibility of self-regulation and management inside these spaces. So anyway, all this suggests the importance of not only conserving human diversity, but cultivating algorithmic diversity for kind of sustained innovation and sustainable bridging inside these spaces, which is to say that you're maintaining enough difference that the collaboration doesn't just corrode and collapse to the center of the collective mean.